La Moldavie, 12 points. Thank you, Sonia.
And the last but not the least, 12 points from Moldova go to Ukraine.
Ukraine, 12 points. Thank you, Olivia.
It's a little bit culture.
And finally, our highest point, 12 points go to Ukraine. Дуже цікаво, дякую.
Diego, Ukraine, 12 points.
Hi, and the 12 points goes to you, dear Sweden.
What? No. There's the songs. It's once a year. Where's my button?
Beautiful girl from Ukraine.
It's a song, like there's songs, and then they go through like 1 point to, like every country will then go to like 1 point to this, 2 points to this, 3 points to this, till they get to 12 points, and this is the summary of just the 12 points. It takes like a few, it's like something like that. Yeah. And everyone's counting, it's like how much? It's like, well, they gave us that much. Well, maybe you should give them, And it's all about it's texting, So the votes are now they're text, or maybe online even. So like people can, from that country can vote. Anyway, just a little bit, Welcome to EE123, lecture 15.
Almost.
Lecture 15. Woo! Okay. It's tough. It's a Friday. So what did we talk about last time? Are you ready? Are you ready to do some sampling? Are we ready? I'm ready to do sampling. Okay, so last time we talked about ideal sampling model, so continuous to digital conversion. We talked about the difference between continuous to digital conversion, between an analog to digital conversion, which is just the wording, but continuous to digital conversion is the ideal one, where analog to digital conversion, we're going to refer to this as the non-ideal case. We did represent things much more simply when we went from x sub c, which is the continuous time signal, to x sub s of t, which is the impulsive version. Okay. Then we went from impulses all the way to discrete by evaluating this impulsive function at n times at those nt's. So evaluating those delta functions at n times t, where they occur. And then we looked at the relationship between capital X sub c of j capital omega to x sub s, j capital omega, and then x e to j omega, which is the discrete time Fourier transform. So this continuous time Fourier transform of the continuous signal, continuous time Fourier transform of the impulsive signal, and then, sorry, I'm still from Wednesday. My voice has not recovered. Every Wednesday my voice is just, it's this 5.5 hours of talking in front of a class that makes it difficult. Sorry about that. So that's the DTFT. We talked about the ideal reconstruction, where how do you reconstruct? You take your signal, which is digital, you create something impulsive out of it, and then you low-pass filter with an ideal filter. Okay, so which is this sinc-based reconstruction. Today we're going to talk about discrete time processing of continuous time signal. So if you have continuous time signal, you're going to sample them, do discrete time processing, and then go back into the continuous domain, and we see the reference. We're going to go quickly through this because it's quite simple. Then we're going to talk about continuous time processing of discrete time signals. It's like, what? Right? And it turns out we're going to spend more time on that one. Strange, right? That's because I like to do things differently. No, there's actually a really nice interpretation, and there's a good reason why to do this, because there's systems in the discrete time that are not obvious what they actually are unless you describe them as their continuous time counterparts. Okay? And we'll talk about that. And then if we have time, we'll talk about downsampling. Lab 2 is starting to come up slowly. We're just making sure that there's no hiccups because of system upgrades and things like this that occurred in the last year on IPython, Notebook, Jupyter, whatever comes out. And so we released, we released one? Part 1, which is about spectrograms. And then part 2 is going to be FM, broadcast FM radio. Okay? So, sweet lab. Okay, ready, set, go. Okay, last time we talked about reconstruction from band-limited signals. If we have the Nyquist theorem says that if x sub c is band-limited, then if you sample, and this is, so this should be, so if you sample at a rate that is just greater than twice the sampling, it's not greater than equal, it's actually just great, then x sub c can be uniquely defined. Do you know why it should be just over? Like it can't be exactly the same? Yeah, so you can look at a sinusoid example. And sinusoids start at 0. And if I sample, what's the rate that I need to sample it? Is basically every half cycle, right? But the problem is that if I sample a sinusoid at every half cycle, 0, 0, 0, doesn't work. For cosine, it works. 1, minus 1, 1, minus 1, right? So you just need a tiny bit over in order to see this change. Okay, that's basically the intuition behind that. Okay, so that's great. The band limitedness is the key for the reconstruction because there's many signal that can go through those measurements, but only one of them is going to be band limited. Okay, and the reconstruction is going to be by taking x of n, converting it into an impulse train. If we look at it in the frequency domain, that's the impulse train, and then in order to, so this will be the Fourier transform of the impulse train, and it has all these replicas. And then if you want to reconstruct the original one, you have to go through a low-pass filter. And if you go through the low-pass filter, you got yourself the perfect reconstruction. Then I mentioned what happens if you have a non-ideal case. In the non-ideal case, when you do sampling, when you want to do anti-aliasing that is non-ideal, in the sampling case, again, I switch back from reconstruction to the sampling part, just because I promised you this demo. In the non-ideal case, if you have a particular signal that is somewhat band-limited, but it's not really band-limited, we're going to apply a anti-aliasing filter, but the anti-aliasing filter has a roll-off, right? And it's not perfect within the band. It's not going to be completely flat, as well as you might have an interference on the side of the band, and that may not be attenuated absolutely. So once you do this, then you will get both distortions of your spectrum, which is going to be weighted both in phase and magnitude by the phase and magnitude response of the anti-aliasing filter, as well as some aliasing that's still going to occur. Okay, so that is always there. The cool thing about DSP is that one thing one could do is oversample a little bit. Then you've got still some aliasing going on, this weighting, but then in the digital domain, you can correct for a lot of those effects. You can correct for the phase, you can correct for the magnitude, and so on and so forth. And that makes this much more powerful than any other system. So you can trade off the quality of the receive chain by just oversampling, and we're going to talk about later in class. I want to do this demo. Again, I set up this SDR, and but it's not working. Of course, it's a demo. Realtek, great. We're going to sample now at 1.8 megahertz. It didn't close. It just moved to the other screen. Okay. And so now you see a spectrum. And I'm going to look at some receiver options here, FFT settings. Yeah, this looks pretty good. Okay. So I'm going to switch to a frequency, and I'm going to turn the sound off. That is a frequency where I'm going to look for my voice. Hey, I think that's the one. Okay. I'm going to take off the antenna. So the gain is reduced. I'm also going to change the gain. So the gain is, it's saturating, of course. Okay, I'm going to change the gain so it's also low. So then you see only the main peak. And then I'm going to look for where it is. Maybe I'll put the antenna now back. One, two, three. 1, 2, 3. 1, 2, 3. Okay, so you can see the spectrum. You can see the spectrum of the FM transmitter that I have. Okay, and what I'm going to do now is I'm going to go away and move outside in frequency. So I'm going to modulate at further away frequencies. Okay? So my center frequency is going to slowly shift away. And I want to see what happens as I move away. So moving, and I'm getting to the edge of the band, right? Moving to the edge of the band, moving to the edge of the band, moving to the edge of the band. Oh, you see it shows up at the other side? But then what happens? I'm moving on and more and more and more and more. Oh, and now it's gone. Right? So effectively now you saw the roll-off of the anti-aliasing filter. Okay? So I'm going to move back. Oh, comes up. And now it shows in the right place. Now, do you see all those things that are going the other way? These are all nonlinearities in what's called images because of just the nonlinearity of the receiver here. I can actually reduce this a little bit. Yeah. Okay, any questions? It's pretty cool, right? Now you can actually measure what is the magnitude response of that filter. If you just listen to a tone, you can kind of move it around and then measure what is the magnitude, actually even the phase response of that tone, and characterize that filter based on this SDR, which is kind of nice. Any questions? So it's a real phenomena that you have to deal with, and you deal with by expanding your bandwidth. If I didn't expand my bandwidth, and I had a pretty high bandwidth of the signal, then, for example, this one, if I only sample at 200 kilohertz, then I would definitely get aliasing coming into the signal of interest. But if I oversample, I can push those away. Okay. So, okay. What else we talked about last time? We talked about reconstruction in the time domain. So, in fact, your low-pass filtering, or the ideal low-pass filtering, is in fact a convolution with the inverse Fourier transform of that low-pass filter, which turns out to be a sinc, trap. Okay, it's just a shifted sinc, and so when you convolve impulse functions with a sinc, you would get basically sincs that are translated and scaled by those impulse functions. Okay? So, in fact, the reconstruction is basically just putting a sinc over each one of your measurements. And that sinc has a nice thing that it has zero crossing exactly on the other measurements. So they don't interfere with each other. Okay? And so on and so forth. And you build yourself your band-limited signal. Now, why is it band-limited? How do I guarantee that it's band limited? How do I know it's band limited? I mean, I shifted those sinks and I added them together. Maybe it's not band limited anymore. Wakey. This is important. Important. I need an answer. So the Fourier transform of, so when I place those sinks on top of each other, right? Why is my signal after that, when I add them all together, band limited? Right, it's linear. It's a linear system. Right? You don't make new frequencies in a linear system. If I have a sum of shifted sinks, if a sink is band limited, and I just shift and add them, I cannot generate new frequencies. It's always going to be band limited. So are they going to be constructively and instructively interfering with each other in the frequency domain because you shift them? Absolutely. But only within the bandwidth that they have, not outside. Okay? So you'd see dropouts in the signal and you could things like this, but that's fine. But you don't get new frequencies. Okay? Hence, if I construct a signal by shifting and scaling sinks, it's going to have a bandwidth of that sinks. That's it. Not anything else. And this is really a way that people in communication generate so-called band-limited, almost band-limited signals, is by convolving with something that has a really fast decay in the frequency domain. So you can take a digital signal of plus and minus ones and then convolve these impulses of plus minus ones with a windowed sink, and then you guarantee to have the frequency response of that windowed sink. Okay, this is how these are generated. Yeah. This has been corrected last time, but I copied the slides from the wrong one. It's sum of sinks. Sorry about that. I corrected this. So I would have given you money for this, but since it was already corrected, but then made mistakes again, you get $1. But that's it, not 2. Reminder to myself, don't put new slides that you already corrected, but you didn't use from the other time. Right? You guys corrected. Sync, because what's sinks? Just sync. I don't know. I'll remove the quotes here. There you go. Okay, so now let's move on and talk about discrete time processing of continuous time signal. This is really something that we always think of, right, when we do this, because what's the power of DSP, right? You have continuous time signal. Instead of having all this like filtering, I can like sample it, do the processing, and then reconstruct something that has like these voice effects and all sorts of like cool stuff, I can do. Or I capture something with my digital camera, I compress it on my computer, and then I go and I show it to you. Exciting, right? Video, all this, stuff that they do in video and things like that. That's great. So you understand that kind of a system. And so let's try to analyze what is the system. I mean, the system now is that you put something continuous in, you get something continuous out. So it is a continuous time signal. Only the processing is done discretely. Right? So the way it works is that you've got a signal coming in, you've got a continuous to digital conversion with some sampling rate, T1. Then you have some linear filtering, shift invariant or something, or maybe not. whatever you're going to do here. And then you're going to do digital to continuous time conversion, maybe even with a different rate. Okay? With a different sampling rate. And then you're going to get continuous timeout. And the question is, if h of n, which has a frequency response of h e to the j omega, is LTI, is the whole system LTI? And if not, can it be LTI? Here's an example. It's I go like, ooh, I record my voice and I play it. I play back. Is it LTI? Like in real time, and then play it. Is that LTI? Actually, probably this is actually what's going on here. So I'm recording my voice. It goes through, it's received, digitized, and then probably play it on the speakers. Is that LTI?
No.
Why not?
I don't think it's time invariant because if you shift the signal.
Yeah, I'm shifting my signal. You hear it?
Yeah, but so in the C to D converter,
Yeah.
if you're multiplying by a chain of deltas, let's say that your signal happens to be positive with those chains, where those chains intersect, but zero otherwise, and then you shift it to them, then you're going to get a zero.
Okay, let me ask this: Is the system from my microphone to the speakers is LTI? Assuming no voice distortions, that voice, it's pretty linear microphone, linear reconstruction, things like that. Is it LTI? It is, right? It is LTI. But would that always be LTI? No. So there's going to be some condition on which this system could be LTI. And the question is what is the condition that it should be LTI? Now ignore nonlinearity of distortions and things like that. Because this is an ideal sample, an ideal reconstruction. Yeah. I actually don't think that's the case. I mean, I can see that I sample my voice at 44 kilohertz. My voice is only 5 kilohertz wide. Then it gets to the computer. It's downsampled, does some processing on 5 kilohertz, and then from 5 kilohertz it goes up to, it downsamples the rate, and then goes and reconstruct at continuous time. So it doesn't have to.
The sampling rates have to not introduce aliasing.
Oh, what if I had aliasing? If I had aliasing, then my reconstruction cannot be LTI because I'm going to be generating new frequencies. Right? I'm going to have stuff that's high frequency that is going to alias into the low frequencies. Right? So my spectrum is not going to be the same. And that's exactly the case. If x of c of xc of t is band limited by the sampling rate, then the effective transfer function or the effective frequency response of the continuous time signal is going to be linear shift invariant. And its frequency response is going to be related to h e to the j omega by omega equals capital omega times t. So, for example, if I have a digital frequency response of h e to the j omega that looks like this, of a 5-length moving average filter, it is periodic from minus pi to pi, right? But once I put that into the system, my effective transfer function, my effective frequency response is going to be one cycle of the frequency response of the discrete case. And it makes sense because when I reconstruct, I low-pass filter it. Right? I low-pass filter and I crop one replica out of it. Okay? So that is going to be the relationship between those two systems. So as long as you don't have aliasing and you have a linear shift invariant system in the discrete domain, you've got yourself a continuous time linear shift invariant system, and you can find its frequency response very simply. Okay? So then, now, if you want to do all this processing, you know how to calculate what will be the effective frequency response in the digital domain. Any questions? In the digital domain, it's not. But it comes out to be.
The previous slide, you said if a pivot was LTI, but
Right.
totally unsampling a pivot is not LTI.
Well, okay. I can upsample and downsample in the digital domain. But when I do the reconstruction, if I still keep, what is the original frequencies are, and I don't stretch it over in time, like I can stretch the samples, but I don't stretch it in time, then it's still LTI. So I can go and, sample my signal at 44 kilohertz, downsample at a 5, do processing, and play it, reconstruct it as if it was 5 kilohertz sampled. If that was true, then I'm good. If I would reconstruct it as 44.1 kilohertz sampled, then my voice is going to be really, really high, and it's going to sounds like a mouse, right? So, okay, but that's the difference. There's again nuances here. Obviously, if I have a discrete time signal and I do upsampling or downsampling, this is not shift invariant. But when I start in a continuous domain and I do some processing and I go to the continuous domain, that could be. Okay, again a nuance. It's a great exam question. Can you remember that, John? For next year. By the way, the second question from the exam was the prelims for this year PhD. Variation of it was the prelim exam for the PhD program. So you're ready if you did well. And if you didn't do well, you could be ready. Okay. So let's talk about something weird. Let's talk about the case where we're going to implement something different. Why? Well, just for the sake of it. Okay. Let's start with a signal. So let's do continuous time processing of discrete signal. Let's take x of n, discrete, and let's reconstruct it with some t. Now let's do some analog processing on it. Right? With some analog frequency response to get yc of t. That's the result. And now we're going to sample it again and get back our signal. Now, the interesting thing is that if this is LTI, it's always LTI. Because there's no aliasing here. There cannot be aliasing here. Let's see if there could be aliasing. You go from here to here, this is band limited. This doesn't generate new frequencies because it's linear shift invariant. I sample a band limited signal. LTI. Okay? It's always LTI. Now, why you even bother with this? I would bother with this because it was really useful to interpret some discrete time systems that have no simple interpretation in the discrete domain. But they're obvious when you think of what is their continuous time counterpart. Okay? So this is a really good tool. And the tool that we're going to use there is, what is upsampling and downsampling? How does this relate to the original signal? What if I modulate my frequency domain by a phase which does not correspond to an integer shift in the time domain? Right? If I compute the DTFT of my signal and I multiply by some linear phase that it does not correspond to an integer shift in the time domain. What does that relate to? I mean, it's not obvious to see what's going on in the discrete domain, but it's obvious when you think of the continuous time. Okay. So again, recall that x of c is basically x of n convolved with a sinc function that is translated. It's convolved by a sinc function that has a width of like a zero crossing at t points, every t seconds. Okay. So now let's look at what's actually going on here. We're going to start derive and see what's the relationship between all of these. You ready? Okay. So x sub c of j omega is the same thing as t times x e to j omega, small omega, where small omega is omega t. This is exactly what I showed you before when you looked at, the reconstruction, right? And it's 0 elsewhere. Because when I went here, I just reconstructed a band-limited signal, right? I reconstructed a band-limited signal. And the band-limited signal has a Fourier transform between that bandwidth that I just reconstructed that is similar to the DTFT of that signal. Okay. All right. Does this make sense? The relationship between omega now is just depending on the sampling rate. Okay. What is our sampling rate? What is t? Now, what is y sub c of j capital omega? That is multiplication of the frequency response with the frequency response of our signal. So the frequency response of the system with the frequency response of our signal. That has to be band limited, because if this is band limited, has zeros outside of a certain bandwidth, then actually no matter what is this, this could have an infinite support. H sub c of j omega. It could have an infinite support, but once you multiply with the signal as band limited, it's just the multiplication is band limited. And then when I sampling is a replication of my continuous time signal, right? Is a replication. And when I replicate over that exact bandwidth, of course I'm not going to get aliasing. And if I'm not going to get aliasing, then I'm going to get a frequency, a DTFT that's 1 over t ycj omega at omega equals small omega over t. So there's not going to be any aliasing. So if you take all of these relationships together, you can come up with what is the y e to the power of j omega, is the shifted replicas, where capital omega is small omega over t. And you get this. And if you combine all of that, you get that yej omega is hcj capital omega, where capital omega is omega over t, multiplied by x e to j omega. And this is really your transfer function, the frequency response. So graphically, if you want to figure out what is the frequency response, here's an example. Let's say this is h sub c of j capital omega. And it's crazy outside of the bandwidth of our reconstruction. crazy, and it's crazy there too, but I don't care. I don't care it's crazy there because my signal doesn't have any support there. It's not going to affect my signal. So if this is h sub c of j omega, my h e to j omega of that discrete to discrete system is really just this portion that is just being replicated. Okay? So this portion from minus omega sub s over 2 to plus omega sub s over 2 will be transformed into minus pi in the discrete domain. The rest don't exist because I don't have signal there. And it's just going to be multiplied by 0. Does this make sense? Yeah.
Can you explain what happens if the C to D and D to C converters have different sampling rates?
I did not talk about sampling rate right now.
Yeah.
If they're going to have a different sampling rate, we're going to have a problem.
Even if both of them are bigger than that.
If we're going to have a different sampling rate, if this is, if this actually has if this has aliasing, let's say this is slower than this one, then we're going to have a problem.
They're both fast enough, but they're different. Does that change it?
I don't think it's going to be LTI anymore. It will be like upsampling or downsampling, effectively. So it's not going to be LTI anymore. It'll be linear if they're fast enough, if there's no aliasing, but they're not going to be LTI. Unless, well, no, they're not going to be LTI. Okay, so here's an example where this is actually interesting. Let's look at this frequency response. Digital frequency response of E minus j omega times delta. And the question is, what is a time domain operation? Well, delta is not an integer. Let's say delta is a half. So normally if delta was like 1 or 2 or 3 or 4 or 5 or 6, that wouldn't be a problem. I would just tell you my signal shifts one sample. But what does it mean? What does it mean? What does it mean to shift one sample? I don't know. How can I shift one sample? I have this array. I tell it, cut in the middle. Like, it's difficult. There was I was listening to this podcast called Reply All. It's something about the internet. And they had this discussion about this guy had played this game, Super Mario 64, and he was able to solve a few levels with only half a click of the button, the A button. And there was a whole discussion how can you do a half a click? I mean, clicks are discrete, right? And he claims that if you press without releasing and over many levels, that counts like half a click. I don't know how to do a half a shift. What's half a shift? It's weird. Well, let's see, how does it look? What is the continuous time representation of that type of system that will give you this? And see, does it make sense at all? Or am I local? So what is the time domain operation? Okay, let's consider the case where my continuous time signal is E minus j capital omega delta t. So a delay of delta t in time, where now this is a fraction as opposed to a full, sampling rate one. Let's see how this relates. If I do that, then I'm going to take x of n, I'm going to reconstruct it. Now it's continuous. Then I'm going to delay by time delta t, and that is continuous, so I don't care. You can delay whatever you want. You can delay by 10 minutes like Berkeley does. Everything. Right? Now it's still continuous time, only delayed by continuous time. And then I'm going to sample it again. Now that makes sense. Right? That makes sense. That makes sense. Does it make sense to you? Okay. So here's how it works. You start with a signal that is, there's two indices here. There's x of n has an n at t. All represent t, 2t, 3t. N equals 0 is 0. N equals 1 is t. You found a bug? You found a bug? Because you look at my slide. Oh, text. Well, what is your text? Oh, yeah. Yeah, I just remind me that I want to show something. What is this text? Okay, all right. Go for it. Remind me? Lucas. Okay. Yeah. So, those are the discrete points. Now what you'll see is that the output is going to look like that. That's what the output is going to look like. And the question is how do you get there? And how you get there is that you reconstruct the continuous time signal, then evaluate it on a delayed grid. But then that will be index 0 of y of t. And then that shows up here. Okay? Does this make sense? The signal continues on. It's like a continuous thing. Does this make sense? So now, that's a great system. So when I do this e to the j omega delta, where delta is not an integer, it's like as if I reconstructed a band-limited signal, shifted it by some delta t, and then resampled it. That is the equivalent. It might not be originally continuous, but that is the equivalent in terms of a continuous time. Yes? What do you mean? Yeah. Yeah, you'll get a shift 1. Right? Absolutely. So when we do all this processing in the discrete time, effectively we are thinking of band-limited signals, as if our signals were originally band-limited. So the operations there then become obvious, because I can theoretically reconstruct them, resample or whatever, do the operation there, and then sample them again. So the thing is, this block diagram is really only an interpretation, right? When I do, if you look at y of c, it's really x of c t minus delta. Okay? So let's see how does it look in just using discrete time processing, because it's a discrete system after all, right? It is a discrete system. So if I look at y of n is equal to yc at evaluated n times t times, right? That is x sub c nt minus t delta. Now what is this? This is my signal x that is convolved with a sinc that is going to then be shifted by t delta, right? This is, if I want to write what is this, this is the sum of xk sinc of t minus kt minus t delta over t. Right? This is a continuous time signal. But it's band limited. I can represent it as samples that are effectively represented by a convolution with sincs. Hence, if you actually stare at this, you see, well, if I have t, this is continuous time, so t minus kt, and I evaluate them when I resample at t equals n times t. So then if I put t equals n times t, you got t, 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 t. All the t's cancel. Of course they cancel, because who cares what is really the time? Because it's all going to be discrete eventually. There's no really time when I do something in the discrete domain. They're indices. So the t's are going to cancel. And I'm going to get that y of n is equal to the sum of x of k multiplied by sinc n minus k minus delta. So effectively now it's a discrete convolution. Right? It's a discrete time convolution, linear or periodic? Obviously linear. Right? There's no periodicity here. It's a linear convolution between the signal sinc n minus delta k minus delta with my x of k. Right? So it's just as simple as that. And if you look at what is then the impulse response of that system, the impulse response is sinc n minus delta. That's the impulse response. That's what we convolve with. And so example as a discrete delta is really a representation of a sampled sinc. If you think about this. So when you look at every discrete delta in the time in the discrete time domain, right? You can also represent it as a sinc that I just sampled. Does this make sense? I sampled a sinc. And so, if I shift that delta by half a sample, I'm just going to be evaluating it on those points. And so effectively, e to the j omega t is really a sinc interpolation of my discrete time signal. So you can think of every impulse in the time domain as representing a sinc. Because this is how would we even go from the discrete to the continuous time, right? How would we do it? We represent as an impulse, and then we convolve with a sinc. That's what is represented. So all the operations that you do are represented using band-limited signals. And so now that's much more, like you can understand now, what does it mean? So if I had an impulse and I say, well, how about I'll shift my impulse by half a sample? Whoa, where do all these measurements come from? Right? Where do all these measurements come from? Obviously, they came from the fact that my delta is not really a delta in the continuous time domain, because if it was, I wouldn't be able to sample it without aliasing. It's really representing a sinc, a band-limited signal. Okay. A similar phenomena happens when we compute the DFT of some sinusoid. At some sinusoids, I'm going to get a deltas in the DFT. But if I just shift the frequency of those sinusoids a little bit so they don't align with the integer, I'm going to get a periodic sinc. Okay? So it's a similar phenomenon in that sense. Because I think of things as representing discrete time sampled band-limited signals. Okay, any questions before? I think we're not going to go to downsampling today. We're going to do downsampling and upsampling next time, which is going to be Monday. Any questions? Yeah. Mm-hmm. This one? Where? Yeah, t equals nt, right?
I got that part, but
You're right. I think you're right. I think you're absolutely right. No, it should be. That's a good bug. Thank you. So it should be a delta here, right? Because I just put NT here. Yeah. Yeah, that was a mistake. And you'll get now your reward. Thank you for this. Wait. No. So we delayed by. Right, that's the delay in time, sorry. That's the delay in time, and that's actually, sorry, that's the derivation. So, this one should be delta t. Absolutely, yeah. Thank you. So it's still a bug. Oh yeah, I was hiding behind it. I just moved it to the left and then it shows up. All right, folks. Have a nice weekend. Homework's due today. There's no homework. There's no homework due today. So have a really nice weekend. What? We're post today.